Assalamualaikum and hi Dr. Hidayah. So my name is Nur Hazima bin Wahab. So the topic that I got is about thermoelectric refrigeration, and for this assignment I will discuss about the improvement in the thermoelectric properties in tin bismuth telluride material, which is as a main topic. So the finding of the density functional theory have verified that a tin bismuth telluride material is an effective and safe material in thermoelectric applications. So the FPLA-PW technique and VN2K code were used to do the computation. Due to its high seatback coefficient value and low heat conductivity, this is the traditional thermoelectric method used in refrigeration and thermoelectric generators. So here we have covered the outcomes of calculation for thermoelectric characteristic using spin orbit coupling and calculation without SOC, which is according to SOC and non-SOC calculation. Change in the band structure occurred and the density of state was clearly described. Due to the thermal energy generated by waste, our ecology has been harmed. So these unused heat energy sources include industrial waste, autos, air conditioning, waste heat from household appliances, as well as heat from our bodies. So thermoelectricity is the only technology that can end these situations. So by optimizing 7 different tin bismuth telluride material combination using first principle calculation, we are able to identify extremely safe and effective material, and we can then use theoretical and computational procedure to evaluate the characteristic of thermoelectric materials. And in order to determine the electrical and thermoelectric characteristic of bismuth, we employ a spin orbit coupling SOC simulations. Alright, so how to conduct this research is, firstly, VN2K code is utilized in the current density functional theory to examine the electrical and thermoelectric characteristic. And number 2 is the full potential linearized augmented plane wave technique was used to run the code and do the computations. And number 3 is solving the Kohn-Sham equation within a self-consistent framework, or we call it SCF. And number 4 is use the Perdue-Burke absorb and generalized gradient for the optimization of the whole structure. And number 5, the energy was set up at 0.001 Ibert, and the K point 1000 was used to measure of 10.9 is for the convergence of the total energy. And the last one is then calculate for the SOF for each material. Apart from that, the thermoelectric characteristic of material were used to estimate by using optimized structural data. And supercell was constructed by using 60 atoms with 29292 type for making the structure of that material by replacing Sn and Vi atom in the crystal lattice of S and Te. And lastly, for this both track code interface to the VN2K code was used to study the thermoelectric characteristic of all these material dependent on the temperature and for SOC calculation. So post-track with SOC was employed. By looking at the figure 3, figure 3 shows that the Fermi energy level F as a horizontal black line due to the presence of SOC and p orbital in the doping concentration S equal to 0.875 combination. All of the WHC, XW and K symmetry points of the brilliance zone have conduction bands that cross the Fermi level, while for the figure 3b shows that the conduction bands cross the Fermi level and that the valence band maximum and minimum meet at the C point, which is below the Fermi energy level, and confirming that SOC is significant in the area of the energy around C point. And we can conclude that this material contains central symmetric point groups due to the Kramer's degeneracy, and each band curve is doubly degenerate in both non-SOC and SOC calculation, which is figure 3F, which is confirmed metallicity. So as we could see that the total DOS for both SOC and non-SOC calculation included in the inner square box and partial density of state DOS for SOC is plotted against energy as shown in figure 4A until G. So from figure 4A, it's observed that the DOS at Fermi level is 0, confirming the material SNTE has semiconducting nature, and around the Fermi level SP and TESP states of the electron contribution become more, and sharp peak observed in valence band only by TES state electron. So due to a change in the system electrical characteristic broke on by the saturation of the p orbital and the bismuth and SN atom, it's evident from all the DOS and PODOS that the Fermi level shift to the conduction band edges after being merged with the bismuth atoms in the SNTE crystal. Figure 5 shows the charge density plot of all 7 combinations of thin bismuth telluride material at ambient conditions. So the charge density plot reflects the bonding nature between these 3 atoms. From figure 5 also, it's observed that the spherical contours around the region of SN, Bi, and Te atom as evident for the strong ionic bonding nature between the atoms also indicates weak covalent nature of the material. In charge density, electronegativity is an important concept. It determines whether the material is ionic or covalent bonding in nature. If the electronegativity difference between the atoms is large, the transfer of charge takes place and the material results in ionic bonding nature. For figure 6A until E and 7A until E, it displays the Seebeck coefficient, electrical conductivity, power factor, electronic thermal conductivity, and figure of merit for all combination of material at 300 and 1000 K temperature with and without SOC. In figure 6A and 7A, the negative sign of Seebeck coefficient value indicates n-type material having majority charge carrier as electron, and positive sign is for p-type materials, and maximum conduction is only due to the holes. So the obtained result of ZT value is maximum for SN for 0.875, bismuth for 0.125 telluride, material both in SOC and non-SOC at 1000 K and at 300 K, while for SN 0.125, BI 0.875 TE, and SN 0.75, BI 0.25 telluride. Material have maximum ZT value due to the maximum value of electrical conductivity and minimum value of electronic thermal conductivity. As conclusion, it's found that within SOC computation, the band structure and DOS produce good result. And for the SN 0.125 with bismuth 0.875 telluride is the most ductile and least hard of the 5 newly researched bismuth doped material. The SN 0.75 with bismuth 0.25 telluride and SN 0.875 by bismuth 0.125 telluride material each attain their ZT limit, and the highest electrical conductivity and lowest electronic thermal conductivity of these two materials make them preferable choice for the thermoelectric application.